Let's next talk about conditional probability and conditional expectation, which is going to form the groundwork for Markov chains, which are one of the main things we're going to study in this course. Just as a point of reference for you to have for now, I've included a table here of probability distributions. This continuous and discrete, all the attributes of them that are going to be relevant to you. They're PDFs, PMFs, CDFs, expectations, and variance. Pretty sure these are all of the distributions that we're going to use in this course, so you can feel free to refer to this as a handy reference whenever you like. We talked before about marginal distributions, which is something that arises when you're talking about joint distributions on two or more random variables. A marginal distribution is what you get if you have a joint distribution for two random variables, let's say x and y, and you're only actually interested in one of them, right? So this is where I've got samples, pairs of things that are coming in. I've got an x and a y, and I say, well, I actually only care about x, right? Disregard the y. And so if you have a joint distribution, f of x and y, as you probably remember, the notation for the marginal distribution has a subscript x or a subscript y, depending on which variable or random variable you're interested in. And the phrase to remember with this is just that if you have a joint distribution and you want the marginal, you just have to get rid of the variable that you're not interested in, and the way you do that is you either sum it out or you integrate it out. We'll do an example here with a discrete distribution involving two dice. We'll do the same example that we did in lecture before. So say I've got a pair of dice here, and I roll them, and I record two things. So in this case here, you can see I've got a 5 and a 1. And we're going to form a joint distribution by writing down the smaller of those two values. That's going to be x, and in this case, that's going to be the 1, the smaller of those two values. And then y is going to be the sum, and in this case, 5 plus 1 is 6. So this would be the point x is equal to 1, y is equal to 6, and you can see that lies right here in the table, like that. And the probability of this happening is 1 on 18. And so what I've also done with this table is I've written out, I've written out the sample space here. I've written out the joint distribution on the x's and y's here, which, as I mentioned before, is not the best example in the world because all the numbers in this joint PMF are either 1/18 or 1/36, so it's not very interesting. But I've also written the marginal PMF on x down here. And I've also written, on y is the one down here, and then on x, I've written it here. So how did I obtain these things? So these values here, for example, in this column, 11 on 36, and so forth, these all came from me simply adding up the entries in these rows, right, and writing those values in there. So that's me adding over all the possible values of y, and then just getting these are the probabilities of the various values that x could take. So this number here, 11 on 36, that tells me if I roll two dice and I only care about the smaller of the two values, then the probability that the smaller of those two values is, for example, 1, would be 11 on 36. Okay, so that's me disregarding y, like I don't care about it. I'm adding over all the possibilities, and I just care about x. Similarly, this distribution down here is just the probability distribution for the sum of what's on two dice from y equals 2 to y equals 12. And we've seen that distribution before, right? It tells you that 7 is the most common thing that you're going to roll. Probability of getting that is 1/6. And so forth. So we've seen this one before. Let me kill some of this out here because I'm going to have to refer to this table later. Okay, so in addition to joint distributions and marginal distributions, there's also something called a conditional distribution, which arises from a joint distribution. And it's related to a marginal distribution, but it does have an important distinction, and it works like this. A conditional distribution is what you get if you know the value of one of the variables. You know that y is that the capital Y is equal to little y, and you just want the distribution on the remaining variable. That's different from a marginal distribution. Marginal distribution says, I don't care about y, I just want to know about x. Conditional distribution says, I've told you what y is, now tell me about x. So those are two different things, but they both involve taking a joint distribution and recovering a distribution on a single random variable. So that's called a conditional distribution, and I've given the formulas for them up here. For the continuous, so notationally, it's a pretty ugly thing. We don't actually use this notation very much, this f with an x given y and as a subscript. I avoid using this because I think it's really ugly. But the way you compute that is you'd say, okay, well, the probability that x is equal to, the probability that random variable x takes on a certain value, little x, if we are given that the random variable y takes on this value, little y, the way you compute that is you just take the joint PMF or PDF for x and y and divide that by the marginal distribution just for y. So that's how you do that. This is how you can work out, if I tell you what y is, then here's the distribution on x. It's with this formula here, and we'll do an example of that in just a minute. So if you've got that, you could also define conditional expectation, right? What's the expected value of x given the value of y? And for the discrete case, what you would do is you would just sum up, you would sum up this expression here. You would sum over all over the x's times the conditional probability on x. As I said, I don't like that notation with the x bar y and the subscript because it's ugly and hard to process visually, and so I would rather think of it like this. You would just say, well, take 1 over the marginal distribution evaluated at y. This is the value of the random variable y that you've been given, and then just sum over all of the values of x times their conditional PMF in the usual way. And for the continuous case, you would do the same thing, but take an integral. I don't expect these formulas to be, to sink in right away. It's hard to digest, so I think the best way to work through this is by examples. So let's go back to those dice with x and y like we had before and see how we work that out. You'll find that this is actually just plug and chug. So what is the probability that x is equal to 2 given that y is equal to 8? So let's go back to that table there just so we see what we're talking about. So we are given that y is equal to 8, which means we're restricting ourselves to this column right here. And so y is equal to 8. It means the sum of the dice shows 8. And so how could that happen? Well, as you see in this table here, there are 3 ways this could happen. You could get the smaller of the two values would be a 2, and the larger value would be a 6. So you could get a 2 and a 6, or the smaller value could be a 3, and the larger value is a 5, or you could have double 4s. Okay, if I can find 4 on these dice here, there it is. Or you could have double 4s, right? And so double 4s, the probability of that occurring is 1 in 36, and the other cases having a 3 or a 2 is 1 in 18. So this is these 3 cases here are what we are interested in, because we've been told that y is equal to 8, and the question asks us what is the probability that x is equal to 2. Okay, so if you plug in the definition that I gave right up here, and boy, have I written a lot of stuff here, so I just scratch all over my slides when I give these talks. If you just evaluate that, you would say, okay, take the joint PMF on top and take the marginal distribution for y on the bottom. So let's go back and do that here. We asked for the probability that x is equal to 2, given that y is equal to 8, and so that is this value right here, which is 1 in 18. And so what that formula said to do is take 1 in 18 and divide it by the marginal distribution for y, which is 5 on 36. Okay, so we just compute that, do the algebra. It's 1/18 on 5 on 36, which is 2/5. So that's how you calculate that. So if I know that 2 dice sum to 8, then the probability that the lesser of those two values is 2 is 2/5. Let's do a conditional expectation example. What's the expected value of x if I tell you that y is equal to 6? Let's go back to that table again and look at what that is referring to. I've told you that y is equal to 6, so let's erase all this here. I've said y is equal to 6, which means that the dice sum to 6, and that means we're interested in these 3 entries there, like that. And we've been asked for the expected value of x, given that this is the case. And so what do? We go back to the slide here, and we say, okay, what is the how do we compute the expectation? Well, you just take 1 over the marginal distribution on y, multiply that by the sum of all of the x's times the joint PMF there. And so what are we going to do? We'll go back to this table, and we'll take 1 over this value here, 5 on 36, and we'll multiply that by the sum of 1 times 1/18 plus 2 times 1/18 plus 3 times 3 on 36, like that, adding those values over. And so you work out that sum, as I just said, and you end up getting 9/5. So given that 2 dice sum to 6, the expected value of the smaller number being shown is 9 on 5. So that's a discrete example of conditional expectation. Let's do a continuous example too. We've got a joint density function that looks like this thing you see here, and it's defined for x and y between 0 and 1. And we're going to ask, what is the conditional density on x given y? And then what is the expected value of x given the value of y? Again, both of these are just going to be plug and chug, but we just want to make sure we're referring to the correct formulas and using them properly. So the conditional distribution on x given the value of y, if you refer back to the slides, it's just exactly equal to this thing here. So it's the joint PDF, which is just this thing here. The joint PDF divided by the marginal PDF on y. And so how do we obtain the marginal value, the marginal PDF on y? You integrate the x out, which is what I'm doing down here in that denominator. So take the PDF and integrate the x out. And you'll notice I'm integrating from 0 to 1 because that's where this distribution is defined. And you get this function here in x and y. So simple as that. For the second part, we've been asked what is the expected value of x if you tell me what y is. And again, you go back through the definition of expected value of x given the value of y. So that's the integral of x times the conditional density evaluated at y, and that turns out to be this integral here, which evaluates to this expression there, 5 minus 4y on 8 minus 6y. So I haven't done anything clever here. I've just applied those formulas that we saw a moment ago. Conditional expectations, you also often see those when you're restricting things to a subset, like what is the expected value of x given that x is less than or equal to t, right? I say, well, I roll some dice here, and I say, I'll tell you, I'm not going to tell you what the numbers are, but I will tell you that the value is less than or equal to 9. Right, so now that you know that the value is less than or equal to 9, you could then work out what the expected value is on those dice, right? Given that it's less than or equal to 9, you know that it's going to be less than 7. So that's a useful thing to determine. For continuous random variables, this is calculated by just working in the definition of conditional expectation based on that. what do? You take 1 over the probability that x is less than or equal to t, and you integrate everything less than or equal to t of the usual expectation integrand, which is x times the density f of x. And that just ends up being this expression over there. So I don't have an example for this one, but again, they're just distributions, or they're just integrals that come from a distribution. So there isn't a lot of interesting stuff to say there. And I've got the proof worked out where you actually would derive this, but this is not a proof-based course, so we don't need to worry about that. This starts to get really interesting when you start using what is called the law of iterated expectation, which I'm going to show here in just a moment. The law of iterated expectations is a useful rule for computing an expected value of something, a random variable, that depends on other random variables. So I could easily give you a probabilistic description of some situation where the expected value would be very hard for you to calculate. The iterated expectation rule, or the law of iterated expectations, it's also called the Tower rule, is a very useful device for taking really complicated looking probability questions and making them simple. So the first thing I'll point out is I tell you, you can look at this expression here and you know what this means. This is the expected value of x given the value of y. Oftentimes you will abbreviate that as just this, expected value of x given y, because we're saying given y, because the other part here, the little equal sign, the equals the little y is a little bit sort of implied. It's like you can tell what this expression means. You're saying expected value of x just given the other variable, which is still random, but whatever, who cares? So here's a useful property of expectations. This is not going to mean anything to you until we work through a few examples that get progressively more and more, I think, impressive. It says the expected value of x is equal to the expected value of the expected value of x given y. And that just means if you want to condition, or if you want to compute the expected value of something, and that something depends on something else, then you condition with respect to the something else, and then compute an expectation of that. Let's do an example, and I can show you what I mean. Let's do a simple example here to illustrate conditional probability. As it says here, you have a stick of length 1. So we'll draw ourselves a stick here that goes from the interval 0 to 1. And you break it off at a point y. So you grab a point y uniformly selected between 0 and 1, and you mark it there. And now you're holding a stick in your hands that has a length y, and you grab that stick and you break it somewhere at a point that we're calling x. And the question asks you, what is the expected position of x here? How big is the stick that's remaining after you break it off, break off 2 chunks of it? And so the thing to make note of here, so y we can understand follows a uniform distribution from 0 to 1, and x follows a uniform distribution from 0 up to y. Right, because y, I think the y one is clear enough, and x has to lie in this interval there, right, between 0 and y. So x follows a uniform distribution from 0 to y, and that y there is random, right? It's a capital Y, which is what makes the problem interesting. So let's apply what we've learned about conditional probability and say, well, if I knew what y was, well, what can I say about this? So the uniform distribution, right, the expected value is just the midpoint. And so we can say, well, if I knew what y was, then the expected value of x given y is just y on 2. Right, because let me make another drawing over here, right? If this is my interval there from 0 to 1, and then I've got y over here, And then if x is uniformly distributed here from 0 to y, then obviously its expected value is just right in the middle, which is y on 2. So if you knew what y was, the expected value of x would be y on 2. And now let's apply this conditional or law of iterated expectation. We have the expected value of x is equal to the expected value of the expected value of x given y. This is precisely that formula that I wrote a moment ago. And so what did we say? We said expected value of x given y is equal to y on 2. So this is the expected value of y on 2. And so what is that? That's 1/2 of the expected value of y. Y follows a uniform distribution from 0 to 1, so expected value of y is, of course, 1/2. And so therefore expected value of x is 1/2 times 1/2, which is 1/4. So that's expected value of x is 1/4, and that's how we calculated that. So the tricky thing here is that I had a random variable y and a random variable x, and x depended on y, and we were only interested in the expected value of x, sort of disregarding y, and we applied this law of iterated expectation to do that. Let's do another example. In fact, we'll do a lot of examples to really drive this point home, because it's really the central, really central to understanding this. And this is an example that involves a deck of cards. So I've got a deck of 52 playing cards here, which I will attempt to give a shuffle like that. Okay, so they're random, whatever. And I've got a pair of dice. And here's what we're going to do. I'm going to roll the dice. I'm going to add the numbers together. In this case, I see the number 6. I'm going to add those two numbers together. I got a 6. And I'm going to take 6 cards out of this deck. Okay, 1, 2, 3, 4, 5, 6. And I'm going to look at those cards, and I'm going to ask how many of those cards happen to be hearts out of these 6. And it happened to be in this case that out of these 6, just by random chance, I happened to get 4, which is pretty unlikely, but it is what it is. Okay, so the outcome of this process is the number 4. Okay, because what I do is as the problem states, I roll the dice, I add those numbers together, and I pull that many cards out of the deck, and then I look at the number of hearts that I see there in that deck. And so let's try and analyze that. So this question asks, what is the expected number of hearts that you will see throughout this process? So in other words, we're saying, when you consider all the possible dice rolls and all that sort of thing, at the end of the day, what is the expected number of hearts that you, the audience, are going to see, right? To make this a little bit more visual, I'm going to sit here and I'll shuffle these cards out of the field of view of the camera, or actually I'll set them off over here, and I'll take these dice and I will roll them, and I won't tell you what is on the dice. Okay, all I'll tell you is I've rolled some number and I'm selecting a certain number of cards, and now I'm discarding everything except for the hearts, and in this case I'm holding 2 hearts. So all you know is that 2 hearts was the outcome, but you don't know what led to it. You don't know what I rolled. That's why. That's this other variable, this hidden thing. Okay, so let's work this one out. And that you would do it like this. What you would say is you go, okay, x will be the number of cards. Sorry, the number of, that's a typo in that slide. It shouldn't be the number of cards. It should be the number of hearts. So let me make a note right there. This number of cards, that word there should say hearts, because the number of cards that you pull is equal to the number of the number on the dice, right? So that definition doesn't make any sense. So x is the x is the number of hearts, and y and y is the number on the 2 dice. And so what is true? So certainly we can say expected value of x given y is equal to y on 4. Why is that true? Well, if I tell you how many cards I'm holding in my hand, then the expected number of hearts is just a quarter of that. That, of course, is just because there's a quarter of the cards in the deck are hearts, and so the expected number of hearts you have is a quarter of the total number of cards. So we have expected value of x given y is equal to y on 4. And so what does this law say? This law says the expected value of x, the expected number of hearts that you eventually are going to see, is again the expected value of the expected value of x given y. That's this thing. And so we just established that expected value of x given y is y on 4. So that's 1/4 of the expected value of y. Now, expected value of y, remember, is just the expected value on rolling 2 dice. If you play a lot of board games, I'm sure you know that the expected value of the roll of 2 dice is 7, right? The range goes from 2 to 12, and it's a symmetric distribution. The expected value is 7, and I've worked out the calculation here because there's a 1/36 chance of seeing 2, there's a 2/36 chance of seeing 3, there's a 3/36 chance of seeing 4, and so on and so forth up to 7, and then back down to 12. Which would indeed leave you with 7, and then divide by 4 to get for the number of hearts. And so 7 on 4, the expected number of hearts that you will see me holding up is 7 on 4 after performing these dice rolls. So that's example number 2. Let's do another example now where the number of random variables is random. So we'll say x1, x2, and so on and so forth are a bunch of independent random variables whose mean is 2. So expected value of each of these x's is 2. And we'll say that the number of samples that I take is going to be random. That's going to be called n, and the mean of n is 4. So I'm going to take a bunch of random variables, each of whose mean is 2, and I'm going to take a bunch of samples of them, but the number of samples I take is random, right? That's like saying the number of, cards I'm holding in my hand is random. The number of samples that I take is random. It's like saying the number of times I roll these dice is random. That's all. We want to know what is the expected sum of x1 through xn, where n is the random number of samples that we take. So the answer is not very surprising. I just want to make sure you see it worked out in this sort of formalism. The expected value of x1 summed through xn, again, using this law of iterated expectation, it's the expected value of the expected value of the sum of these things, the sum of the x's, given the value of n, given the number of attempts that you're making here. So what is the expected value of x1 summed through xn given n? Well, that's n times expected value of x1. Why x1? x1 because all of these random samples are independent and they come from the same distribution. And so the expected value of x1 is equal to the expected value of x2, and so on and so forth. And so, in fact, let me just write this out to make sure this is totally clear. Expected value of x1 summed up through expected value of xn is equal to expected value of x1 summed up through expected value of xn, like that. And then remember we said that all of these x's are independent random variables with mean 2, which means each one of these is just 2 everywhere. And so therefore this thing put together, the expected sum is 2 times n. And so therefore the expected value of the sum of everything is just expected value of x1 summed through plus xn is equal to the expected value of 2n. And we know that n has a mean of 4, and therefore This is just 2 times expected value of n, which is 8. Not a very nice example, but the really cool one is the one we're going to do next. Let's do another example, and this one is really cool. You have a miner who we'll draw right here, and this miner is trapped in a mine, and this mine has 3 doors in it. So here's door 1, and door 2, and door 3. And these doors work as follows. So door number 1 takes you to a tunnel, and you leave. There's after 2 hours. So you exit, I'll say. Okay, door 1 is victory. Okay, door 2 leads to a tunnel that takes him right back where he started after 3 hours of travel. So I'll do a little 3. In fact, let me make a note. This is 2 hours, and this is 3 hours. Okay, 2 is no good. 2 is it takes you back where you started after you waste 3 hours of running around. And door 3 is even worse. Door 3 takes him right back where he started with 5 hours of travel. Okay, and so we're going to say this miner doesn't learn from his mistakes. He's always, every time he shows up, maybe he doesn't realize that it's the same set of doors that he's seeing. So anytime he sees a set of doors, he just picks one uniformly at random. And this question asks, what is the expected length of time until that miner reaches safety, right? Well, this is a very hard question because we don't know how many times the miner is going to be stuck in this loop, right? The expected number of times the miner takes, it depends on how many times he circles back through doors 2 and 3. And so this sounds like a hard question, and it kind of is, although we're going to show how to work through that using this law of iterated expectation, which is kind of neat. So we'll work through it like this. Well, at x, not surprisingly, will be the time until he reaches safety. And then we'll say that y will be the door that he initially chooses. So that's 1, 2, or 3. So I'll make a little note right here. So we'll do this. Expected value of x. Again, first we'll just start by writing that law of iterated expectation out. So expected value of x is equal to expected value of x given y. And so what does that mean? So what is the expected value of x given y here? Well, y is the door that the miner chooses on his first attempt. Okay, y is the first door that he chooses. So what is expected value of x given y? Well, it's the expected value of x taken over each of these 3 outcomes. So it's 1/3 times expected value of x given that y is 1 plus 1/3 times expected value of x given that y is equal to 2 plus 1/3 times expected value x given that y is equal to 3. And I am running out of space there, unfortunately. Okay, but that's just me copying down the contents of this slide. Okay, so let's look at these more carefully here. What is expected value of x given that y is equal to 1? Okay, that's saying what's the expected amount of time until the miner reaches safety if the first door he chooses is 1? Well, 1 is the good door, right? Y equals 1, that's the good door that takes you to the exit. And so then, of course, the expected value is just 2. Okay, and now that's all well and good, but now let's do the more interesting ones. What is the expected value of x given that y is equal to 2? Let's try that one. Given that y is equal to 2, what is that? Well, what is going to happen when you do that? So the miner chooses door number 2, which means that the miner is certainly going to spend 3 hours in transit because he's walking through that tunnel. We know that he's committed to that. And then what's going to happen? Then, after that miner spends that 3 hours walking through that tunnel, he's right back where he started. And so he's back in a position where he's exactly the way he was before, but he's wasted 3 hours. And so his expected distance going forward is just the same that it was before, but plus this 3 here. So I claim that the expected value of x, given that y is equal to 2, is just 3 plus the expected value of x. Again, the idea here is just that he's done nothing but waste 3 hours. So therefore, the expected value of x, given that y is equal to 2, is just the 3 hours that he's punished for taking door number 2, plus the expected value of x. And by equivalent reasoning, the expected value of x, given that y is equal to 3, is going to be the same principle, but with 5 hours instead of 3. So 5 plus expected value of x, like that. Okay, so now I claim that what we can do is we can solve for x, because I can say what I said. I wrote this earlier formula here that expected value of x is equal to this expression over here. Let me work that one out. In fact, actually, I'll make some adjustments to this formula here, and then we'll work it down here below. So I said expected value of x is equal to this summation here, and we said, okay, expected value of x given that y is equal to 1, that's 2. Expected value of x given that y is equal to 2 is 3 plus expected value of x. And I know you probably can't read much of this, so I'm going to copy it all down as well. And then finally, this one here, expected value of x given y is equal to 3. I'll do a brace over like that. That's 5 plus expected value of x. Okay, let me copy this over down so you can see everything more legibly. Expected value of x is equal to, I'm just going to copy these 3 terms, now substituting these expressions here as I just did. And so that'll be expected value of x is equal to 1/3 times 2 plus 1/3 times 3 plus expected value of x. That's this part here, and I just did that one. And plus 1/3 times 1/5 plus expected value of x, which is this one here. Okay? So you'll notice here I've got expected value of x on the left side of the equation and on the right-hand side. So this doesn't tell me what expected value of x is, right? I would have been much happier if I had expected value of x is equal to 19. I'd be like, yeah, okay, good, 19, I'm done. But I don't have that. I have expected value of x is equal to some other function here of expected value of x. But what's cool here, the really amazing thing, is that you can solve for expected value of x from this equation, right? It's just a linear function. If we instead of writing expected value of x everywhere, I just write, say, the letter q. I'd have q is equal to 2/3 plus 1/3 times 3 plus q plus 1/3 times 5 plus q. I can totally solve that. That's like middle school algebra. And you work that out and you can solve it, and you find that the answer is that the expected value of x is equal to 10. So that is a very sort of counterintuitive or difficult example of the law of iterated expectations being used to work something out that on the surface looks very, very difficult. The problem still looks hard, and I can tell you that the silver lining is that once we get into Markov chains, this problem is going to be really easy for you. So if you don't find my reasoning here particularly compelling, once you see it in the Markov perspective, everything is going to change. Let's do another example. This is one that involves consecutive trials of an experiment, and it looks like this. In this example here, you're conducting a bunch of independent trials, each of which has a success probability p, and you're performing these trials over and over again until you see k consecutive successes in a row. We want to know the mean number of necessary trials. What do I mean by this? Let's say I have one die here, and I'm going to roll it, and I tell you I'm going to sit here and I'm going to keep rolling this die. I'm going to keep rolling it until I roll the number 6 4 times in a row. Let's say I tell you I'm going to keep rolling this until the number 6 pops up 4 times in a row. I'm going to sit here all day until that happens. And this question is asking, what is the mean number of necessary trials, the mean number of rolls I need to make on the average for that to happen? So in this the die rolling example, P would be 1/6 because I have a 1 in 6 probability of rolling a 6, and K would be 4 because I just said I'm interested in looking for I'm going to roll until I see the number 6 4 times in a row. So that's the significance of those two numbers. So this one sounds really hard. When you try to work it out without using conditional probability, it gets to be a very unpleasant mess. But when you work it out with conditional probability, actually it's quite nice. Notationally, we're going to work as follows. So NK is a random number. It's the number of attempts you need to get K consecutive successes. So NK is just the number that we're interested in, right? The number that we're taking the expected value of. We're going to call that N sub K. We want the expected value of N sub K, and this is where conditional expectation starts to become interesting, because one of the tricks that you do, or one of the big tricks that makes these kinds of arguments work, is as you've seen in the previous examples, I would have like a variable x and a variable y, and then you would work out expected value of x given y. This is an example where you haven't been given an x or a y. What you're going to do here, you're working out N sub K, and you have to sort of figure out what the right other variable y is that you want to condition on. And this becomes this is a very tricky thing. This is the really hard part about this subject, but it also is quite rewarding. So we're going to look at NK, which is the number of rolls until we get our K success, or K consecutive successes. And we're going to look at this and we're going to condition on NK minus 1. So we're going to say, okay, we're going to talk about the number of attempts for K consecutive successes, and we're going to talk about that in terms of the number of attempts that you need for K minus 1 successes. All right, and so the formula that I've written here is expected value of NK. Again, this is just the law of iterated expectations. The expected value of NK is just the expectation of NK given NK minus 1. Okay, so we're going to talk about the number of rolls for K consecutive successes in terms of the number of rolls that it took for me to get K minus 1 consecutive successes. And there's a pretty intuitive recursive relationship here, and it looks like this. So if I tell you what NK minus 1 was, if I tell you NK minus 1 was 35, right? That's how many attempts it took for me to get, K minus 1 consecutive successes. Then what is expected value of NK? Well, you've already rolled NK minus 1 times, right? This is how many times you've rolled. So the way to think about this is that you've just rolled the dice and you've just finally seen K minus 1 consecutive successes. Okay, that's NK minus 1 right there. You've just seen that. So how many rolls are you going to need in total to get K consecutive successes, not K minus 1? Well, it's at least 1 because you've got to roll the dice, right? And once you do that, one of two things could happen. There's a probability of P that you'll succeed, right? If I'm looking for four sixes and I've gotten 3 6s, then there's a 1 in 6 probability, a P equals 1 in 6 probability that my next roll will also be a 6, and then I'll be happy and I'll be done. But there's a 1 minus P probability that I will fail, that I'll roll something else, and what does that do? That resets everything, right? Those K minus 1 successes that I've seen are useless to me now because I've broken that pattern. So there's a 1 minus P probability that I just end up right back where I started, which is expected value of N sub K. All right, so that's the reasoning there. And so what do you get? Well, you can just work out the algebra then. that you get expected value of nk, you apply the law of iterated expectation, and as I just worked out here, this expression there, I substitute in there. So I get this big, long, crazy thing. Use linearity of expectation to move these expectation operators around. And then what you end up with is an equation here for expected value of nk in terms of expected value of nk minus 1. So you end up with this thing here. Expected value of nk is equal to 1 plus expected value of nk minus 1 plus 1 minus p times expected value of nk. That turns out to be what's called a recurrence relation. You haven't learned those before. You probably haven't. And if you have, you've probably forgotten them, which is completely fine. I will tell you that there is a solution to that. You could plug it into Mathematica or Wolfram Alpha or Maple if you like, and you'd find that it turns out that the solution looks like this. Expected value of nk is equal to the sum of 1 over p to the I from I equals 1 to k. And so that's the expected number of attempts that you're going to need.